this lecture, we're going to be talking about probability rectangles. Now, at some point, you've probably seen things like Venn diagrams, where you have two circles that intersect, something like this, or you've seen tree diagrams in the context of probability. Now, to me, these methods of computing probabilities are oftentimes confusing, they're inefficient, and they lack conceptual understanding. Whenever I use these methods, I would most likely get the answer wrong because I just wasn't aware of what I was doing. Now, I'm going to show you guys a way of computing probabilities that's going to be different. But to me, when I saw someone show me these probability rectangles, I all of a sudden understood how to calculate any probability. So we're going to be within the context of a deck of 5 cards. And I'm going to draw everything on this whiteboard in a second. But the idea is we're going to be drawing cards from this deck and predicting what we're going to be drawing. We might draw 1 or 2 cards. We might replace the cards. We might not replace the cards. And so the idea is, how can we understand all of those different scenarios without memorizing all the different formulas to use within every single different context? And so that is what probability rectangles are for. So let me set up the problem for you. The idea is there are 5 cards. Now, these are not the actual probability rectangles, although they are rectangles. These are supposed to signify some cards that are in a deck, and they're shuffled. Now, the idea is we're going to have one red and a red 2, and then we're going to also have a blue 1, a blue 2, and a blue 3. Let's make that 3 a little better. Now, we're going to take these cards, and we're going to shuffle them. And we're going to draw from this deck. And the question is, for example, what is the probability of drawing a 1? Now, this is a rather easy question to answer. There are 2 1s out of 5 options. And so therefore, since all options are equally likely, the probability of drawing a 1 is 2/5, or 40%, if you will, or 0.4. Now, that being said, what if we get into more complex problems? Like, for example, what's the probability of drawing 2 1s in a row? Well, that's a rather complicated question. I was taught that you would do 2/5 times 1/4. Now, if you're not familiar with how I calculated this, most teachers would resort to, well, just draw a Venn diagram, or list all the possible outcomes, or maybe draw a tree diagram. But to me, it just seems so weird that we're just multiplying 2 fractions. And there's no reason as to why we're multiplying these fractions. Another question I might ask is, what's the probability of drawing either a 1 or a 2? And so people would say, well, there's 2 1s, so it would be 2/5, plus there's only 1 2, so 1/5. And so we would get 3/5 of draw. There is a 60% chance, or 0.6 of the time, you're going to draw either a 1 or a 2. But this really begs the question, where does this come from? Why in some cases do we add, in some cases do we multiply? And frankly, some scenarios, we mix the two, and it gets even more complicated. And so what I'm really wondering is, how can we make a decent understanding of how this works? Well, there is a way of understanding how this works. Let's start with the first question, and then we're going to slowly make the questions harder and harder, and you'll notice that the solutions don't actually become harder using probability rectangles. It's pretty awesome. Let me show you. So here's the idea. Imagine this giant rectangle. This rectangle includes tons and tons of people. And I'm going to draw these people by just drawing a bunch of dots. Now, these people are all going to draw cards from this deck. And we're going to find what is the probability that they draw a 1. Now, we already know the answer to this. That's an easy question. But in order to understand probability rectangles, we're going to start easy and work our way up. So here's all of our people. All of these people are in a group. And technically, I drew a bunch of dots, but you can imagine many, 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 many more dots here. So all of these people are confronted with 5 cards. what I mean by that is I'm approaching every individual and offering every individual 5 cards. Now it's shuffled, so they can't tell what they're going to draw. There's no way they know. And the idea is I want to know what the probability of them drawing a 1 is. So the goal is to find the probability of drawing a 1. A 1. So how do we do that? Well, you can imagine that some of these members within this group, some of these members are going to draw a red 1. Other members are going to draw a red 2. Other members are going to draw a blue 1. Some members are going to draw a blue 2, and some members are going to draw a blue 3. And the idea is we're going to organize this entire group into 5 sections. Now, we would expect to see that these sections are all equally sized because it's equally likely to draw any one of these 5 cards. So the idea is we're going to be splitting up our rectangle into 5 sections. I'm going to try to do this as best as possible. 1, 2, 3, 4, 5. So the idea is we partitioned our group into the ones who drew the red 1. Some of them drew a red 2. Some of them drew a blue 1, blue 2, and blue 3. Now, by the law of large numbers, if we have a big enough sample size here, big enough experiments, then we should see a pretty decently equally sized sectioning of this entire group. Now, one of these groups is going to be represented by a red 1. One of these groups is going to be represented by the red 2, and then the blue 1, blue 2, and blue 3. So the idea is that this group right here, all of these people are specifically the people that when they drew their card, they drew the blue 3. So those are the people that drew the blue 3, and so on. So here we have our group, and now we want to figure out what's the probability of drawing a 1. Well, first let's determine who drew a 1. It looks as though, let me use a different color, this group drew a 1, and this group drew a 1. Now, each of these sections represents 1/5 of the entire population here. And so in this case, we have the probability of drawing a 1 as being 2/5, meaning that if you have enough people, 2/5 of them are going to be drawing either the red 1 or the blue 1. Now that might seem a little bit overly simplified, but this problem actually becomes, this way of solving probabilities becomes rather useful when we get into more complex scenarios. Now, if you notice, by the way, we did 1/5 plus 1/5. In elementary school, you're taught that you're just supposed to add these probabilities, but you're not necessarily taught why. Whereas in this scenario with probability rectangles, you understand why it's 1/5, 1/5 makes 2/5. And you got to add them because you're finding the total proportion of the population that drew a 1. Let's make a problem that's a lot more difficult. So I need to undo a little bit. Let's find the probability of drawing. Let's draw a 1 and then a 2 with replacement. Now, doing this problem is not too hard. You might be able to solve this problem, but oftentimes many high schools and college students cannot solve this problem. And so let's work through this using the probability rectangles method. Again, the idea is that this entire group of people is segmented into 5 equally sized portions. The group that drew the red 1 first, the group that drew the red 2 first, the group that drew the blue 1 first, blue 2, and blue 3. So this is my red 1 group, my red 2 group, and then my other 3 groups over here. So again, this entire group of people drew the blue 3. I organized them in this sort of way. And again, these are supposed to be equally sized. Now the idea is I'm wondering what's the probability of drawing a 1 and then a 2. Now so far my population has all drawn 1 card, but I want my population to draw 2 cards. So I'm going to partition every rectangle again. Now the idea is there has been replacement. So each of these people are now shown 5 cards again. Now let's talk about the ones who drew a red 1. How many cards are they shown? Well, they're shown 5 cards. That's a relevant question. We'll get into that. We'll get into why it's relevant later on. But again, they're shown 5 cards. And so this group is split up into 5 equally sized pieces. Again, all of these drew a red 1 first. And so the idea is, let's say maybe these guys drew a red 1 again. These guys drew a red 2. These guys drew a blue 1, blue 2, and blue 3. And the idea is this actually applies to every single group here. Let's take a look at, for example, maybe make this a little bit neater, or at least attempt to. Let's take, for example, the ones who drew the blue 2 first. Their group is going to be partitioned into 5 equally sized groups, where one of them drew a red 1, or one subgroup drew a red 1, another subgroup drew a red 2, and so on. Blue 1, blue 2, blue 3. And this applies to every single group here. And then red 1, red 2, red 1, red 2, red 1, red 2. And so let's take a look at one of these little mini rectangles and try to understand what it means. Let's take a look at this one. Oop, that's not really clear. Let's take a look at this one right here. So this guy is in this column, meaning that he drew, or he or she, drew a blue 1 first. Then they drew a blue 1 again. So this group represents all the population that drew a blue 1 2 times in a row. Not a very large portion. Now the question is, what is the probability that you draw a 1 and then a 2 with replacement? So let's find all the people that drew a 1 and then a 2. Now first off, you have to draw a 1 first. So if you didn't draw a 1, then I really don't care about you. And let's use a different color. Let's use maybe green. No, green. Yeah, let's do green. So let's ignore this group for a second. Let's ignore this group, because they didn't draw a 1 first. And let's ignore this group. They didn't draw a 1 first. If you didn't draw a 1, then you're automatically eliminated. And now we're going to try to figure out, of the people who drew a 1 first, how many of them drew a 2? And the answer specifically, let's use a different color. Let's use purple. This group drew a 2. This group drew a 2. Make that a little bit nicer. This group drew a 2, and this group drew a 2. So four groups in total drew a 1 and then a 2. Now, each of these groups are equally sized, and each group represents, this is a fifth of this entire group. And this entire group is a fifth of the entire population. And so each of these mini rectangles that you see here, every single one of them is actually a fifth of the whole population. Or in other words, there are 25 equally sized little mini rectangles in this entire population. And 4 of them have satisfied this condition. That means that the probability of drawing a 1 and then a 2 without replacement is 4 out of 25. And voila, we're done. We don't need to do any like multiplication or addition. Everything's kind of already conceptual here. And so this actually makes math really easy to, or at least probability, really easy to compute. And it makes sense because we're trying to figure out what portion of the group drew a 1 and then a 2. Now that being said, let's get into a more complicated problem, a much more complicated problem. I'm gonna have to undo. Actually, I can just erase everything. No, I'm gonna undo everything. It's gonna take me a little bit of time here, but we're gonna get into a problem that is far more complex. And I guess it's not going to work, which is fine. So I'm gonna have to redraw my 5 rectangles here. I have a blue 1, blue 2, blue 3, red 1, and red 2. Now, typically when you do probability rectangles, you do not need to draw the dots. It's kind of pointless to draw the dots because you can just imagine there's just like this infinitely many dots or whatever in this rectangle, and you're breaking up the group. All right, so we want to figure out in this problem, what is the probability of drawing a blue then a 1. Now, if you're good at math, maybe you've done probability, I actually challenge you, pause the video and attempt this problem. I have yet to find a single one of my students being able to solve this problem without the use of probability rectangles. So use your tree diagrams, use your Venn diagrams. Most math teachers can't solve this problem. Here's why. The reason is because when you draw a blue, what blue cards can you draw? You can draw blue 3, blue 2, blue 1. Now, if you draw a blue 3, how many 1s are there? Well, there are 2 of them. But if you draw a blue 1, how many 1s are there? Or in that case, there's only 1 left. So sometimes there are 2 1s, sometimes there's only 1 1s. And so do you multiply? Do you add? Do you add and multiply? Do you multiply then add? How do you do this? And to me, being completely procedural about it is like the worst thing you can do to tackle this problem. So let's use probability rectangles. Now that being said, I should have clarified that this is without replacement. So we are not replacing any of these cards. The idea is when you draw a card, you're going to put that card to the side and you're only going to be confronted with 4 cards for the second decision. So you have to draw a blue and then without replacement, draw a 1. That's why I was saying, you know, some cases you might only have 1 1, some cases you might have 2 1s. It just depends on what you draw. Now let's use probability rectangles here. Now, when you are confronted with your first decision, there are 5 different options. So we're going to segment our population into 5 different groups. And again, these people drew a red 1, a red 2. These people drew a blue 1, blue 2, and a blue 3. Now, for those who drew the red 1 here, how many cards are they confronted with? They're confronted with 4 cards, because keep in mind, they drew a red 1, they put it off to the side, and now they have 4 cards. Now, what are those 4 cards? Well, those 4 cards are specifically a red 2, not a red 1, the red 1 was already drawn and put to the side, a blue 1, a blue 2, and a blue 3. These are the only 4 options left. And so of the people who drew a red 1, that group is going to get segmented into 4 different groups. Again, some of which drew a red 2, some of which drew a blue 1, some of which drew a blue 2, and blue 3, and so on. And this is the case for all different of these. Every single one of these cases. For the red 2, I can't talk right now. I don't know why. I'm sorry. For the red 2, this group is going to get segmented into 4 groups as well. However, they're going to be confronted with 4 different cards than the group 1, with the red 1 here. These guys are going to be confronted with either a red 1, a blue 1, a blue 2, or a blue 3. Because keep in mind, they drew the red 2. That was the first card they drew. And so the red 2 is no longer in that deck. Now, what about the other groups? Well, the people who drew the blue 1, they're going to be split up into 4 groups. After you draw a red 1, you could draw a blue 1. You could draw a red 1, a red 2, or a blue 2, or a blue 3. With the blue 2, you could draw maybe a red 1, a red 2. You could draw a blue 1, or a blue 3. You can't draw a blue 2, though, because you've already drawn a blue 2. And then blue 3 is going to be split up into groups that draw a red 1, a red 2, or a blue 1 and a blue 2. And so this is how the population would be split up. The population would be split up into a total of 20 equally sized pieces. As you can see, they're all equally sized, and there are 20 pieces. So let's take a look at one of these pieces and try to interpret what happened here. This subgroup right here first drew a blue 1, and then they drew a blue 2. And maybe this group right here drew a red 2 and then a blue 2. But if you notice, there are no repeats in this group. No one drew the same card 2 times in a row, because when you draw a card, you don't replace it, and so it's no longer in the deck. Now, that being said, The question is, what's the probability that you draw a blue and then a 1 without replacement? And so in this case, let's figure out who drew a blue and who didn't. If you drew a red 1, you definitely did not draw a blue. So these guys are not going to satisfy this entire condition here. Same thing goes for the red 2 group. However, all of these guys drew a blue 1, so they passed the first part of the test. Now we're going to see of these people, which of them drew a 1. And that happens to be this subgroup, this group. Here, let's use a different color to make it a little bit easier to see. This group, this group, this group, this group, and this group. And so in total, that is 5 groups out of the total 20 groups. And that is the probability. We're done. We didn't have to multiply. We didn't have to add. We actually got rid of the math, and we're able to conceptually understand what happened with our groups. Now, this takes some time to adjust to. However, again, you're not memorizing to multiply. You're not memorizing to add. You don't have to learn the multiplicative rule of probability or the additive rule of probability, or that whenever you use the word and, you use multiplication, but only if the two events are independent of each other, in which case in this scenario, the two events of drawing the first card and drawing the second card are not independent because it's without replacement. The problems get really tough, guys. And probability rectangles make things a lot easier. Anyways, thank you guys so much. I really hope to see people using this method because it's just totally awesome.